Okay, welcome to lecture here. So last time we finished up that last chapter that's going to be on the exam on Tuesday. A reminder as well, we do have a quiz today at the start of lab on titrations and buffers. And obviously we'll do lab afterwards. All right, so we're then moving on to what we got here. I think chapter 16, and we're going to kind of change gears a little bit. So we've just sort of finished, I would say, I don't want to say the hardest part, but the most difficult in terms of conceptual part of the course. We're now going to kind of be coming back down the hill, I guess, if you want to think about it that way, into more less conceptual sort of understanding and stuff like that, a little bit more of, kind of pick the right formulas and plug and chug and that type of stuff. So, um, there's still obviously some conceptual parts of it, but it's a little bit more kind of straightforward. Not a lot of ice tables per se and stuff like that. So, we're kind of changing gears just a little bit here. So, again, this is obviously not on the next exam here. So it'll be on the exam. I guess that would be three information. So what we're talking about in this chapter is really kind of thermodynamics. Whoops, come back. We're talking about thermodynamics in this chapter, and the idea behind sort of thermodynamics is sort of whether or not a reaction sort of takes place. So earlier on, we really did talk about kinetics, and when we deal with kinetics, we're really talking about in kinetics, as we did then, how fast or how slow perhaps a reaction will proceed. Here, when we talk about sort of thermodynamics, what we're really referring to is the idea of really whether or not a reaction will actually occur. Will it be spontaneous? And will the reaction under those conditions, actually sort of happen? Now, there's a few different parts sort of to thermodynamics. Excuse me. One part you already sort of learned in probably Chem 50 in the previous class, and that was stuff involving energy, and that's like delta H. And remember, delta H, right, is our enthalpy. And as we've talked about before, if the delta H value is positive, it's an endothermic reaction. Again, if our delta H is negative, it's a exothermic reaction. So delta H or enthalpy again deals with sort of the heat. It also deals with sort of the first law of thermodynamics, which you learned probably last semester. And again, maybe you don't recall it be calling that or called the first law of thermodynamics, but sort of the conservation of energy idea, right? So we talked about energy, and energy cannot be sort of created nor destroyed, but it can be sort of transformed from one form to the next. And there's sort of a balance, right, in terms of energy. If somebody sort of gives off a certain amount of energy, something else basically absorbs that amount of energy, sort of that kind of system surrounding idea of in terms of energy. So in this chapter, we're going to kind of build on delta H, and we're going to talk about some other thermodynamic type properties like entropy, free energy. Entropy, as we will see, is actually delta S, and that again is the entropy, not the enthalpy. Kind of sounds the same. Free energy is really Gibbs free energy, which is delta G. And of course, we cannot leave our good friend equilibrium out. So towards the end, we will kind of tie everything a little bit back to the equilibrium constant that we've been talking about. So first off, let's talk a little bit about spontaneous processes and things that occur. And a couple of things. First off, let's talk about sort of the idea of spontaneous. And sometimes, again, people have a wrong understanding or a wrong conception about sort of what spontaneous means. So sometimes people in this sort of context think about spontaneous as meaning, oh, it's going to happen super fast, right? We kind of think about, oh, it's just happening really quick, it's spontaneous. And really, that's not necessarily what we're looking at, again, in sort of these properties here that we're exploring. We're looking at the idea of spontaneity as the idea that, yes, under these conditions, we would expect a reaction to occur. Do we know how fast it occurs? Do we know how slow it occurs? We really don't know. And again, that's more what kinetics deals with, is sort of how fast or slow. But here again in thermodynamics, we're just really dealing with that simple idea of, okay, this reaction is spontaneous, which means could be really fast, could take all day to do, but under these conditions, regardless of how fast or slow, we would expect this sort of reaction to sort of occur. And again, that's what we sort of mean when we talk about it being spontaneous. Obviously, there's a lot of processes that we're familiar with that are spontaneous. Waterfall runs downhill, right? Water goes down, doesn't go up, hopefully. We have sugar that dissolves in coffee at 1 atmosphere and basically standard pressure. Water does freeze at 0 degrees, it melts above zero. When we talk about kind of the flow of heat, it always moves sort of from the hotter object to the colder object. Again, the hotter guy gets cooler, cooler guy warms up. They happen to be sort of in an insulated sort of container. They'll meet somewhere halfway in terms of temperature usually. Um, Iron exposed to oxygen will form basically rust. Basically, those are the three things you need to make rust: some iron, oxygen, a little bit of moisture, and you're good to go in terms of making rust. Obviously, we have our skiers there, and a couple of things. One thing is spontaneous. Clearly, if you're at the top of the hill there and you're coming down, it's pretty much spontaneously going to happen, right? You don't have to do much; just kind of go over the hill. Going back up the hill and probably scaring the person that's coming down the hill, I imagine here, obviously is not a spontaneous process, right? You can't just stand at the bottom of the hill and get to the top, right? Just spontaneously going to happen. You actually have to supply some energy and do some work to get you up the hill. And that's sort of what we're talking about here. Obviously, she's skiing up the hill, doing some work to kind of go backwards. Some other examples here of some things that are spontaneous and non-spontaneous. Whoops. I'm not sure how well it came out, but this is basically a two glass cylinders that are connected by kind of a valve right about there. And obviously, if we open the valve spontaneously, everybody that's filling the left-hand side, the pressure is going to be kind of released, and they're going to come over into the other side and fill it up sort of spontaneously. If we kind of started with everybody on both sides there and we opened the valve, they're probably not spontaneously all going to decide, let's just all go over here on vacation to this side. It's probably not going to really happen. You would probably have to do something maybe to this side to force everybody over to the left-hand side. And obviously that is not sort of a spontaneous process. You're doing some type of external work to get those guys over there. And it would be considered really a obviously non-spontaneous process. So when we talk about heat and energy and enthalpy and whether or not a reaction is sort of exothermic, does a reaction being exothermic really mean that the reaction will perhaps proceed spontaneously? And what we look at here is some spontaneous reactions. So we got really a combustion reaction there with methane, has a delta H of minus 890 kilojoules, again, meaning that it's exothermic, which we would expect, right, energy to be given off. The formation of water there, also exothermic. But there are some processes down here that actually are more endothermic. We see we got a positive delta G for water in the solid state going to water in the liquid state. That is basically an ice cube, right? Melting. Also, the process where we dissolve an ionic compound in water, also we can see here a positive delta H. So both of these things would occur spontaneously, right? We know if we take out an ice cube right from the freezer, put it out on the bench and kind of not do anything to it, it is spontaneously going to start to melt because it's really picking up heat and energy from the surroundings, right? It's causing that ice to melt. You don't have to do anything to it. It will just sort of do it on its own in that sense. And what this tells us is, although enthalpy may play an important role in whether or not a reaction is spontaneous, it does not always necessarily guarantee that a reaction is going to be spontaneous if you have a negative delta H or an exothermic reaction. It could definitely help in terms of spontaneity. It oftentimes will favor it being a spontaneous reaction. But what we see here on the bottom is there's absolutely two positive delta H's. And again, those reactions as well do occur spontaneously. So although it's a good sort of step in terms of perhaps the reaction being spontaneous, if you have a negative delta H, again, it doesn't necessarily always guarantee that if you have a positive delta H that reaction would not be spontaneous. There are other conditions that we have to look at. And one important sort of thermodynamic conditions is what we're going to talk about here. And this is what is known as entropy. And entropy is basically a measure of randomness or disorder of a system. So when we talk about entropy, we oftentimes talk about the idea of change in entropy. So entropy is a little different than some things that we normally think about in terms of, say, the sign of the change in entropy, whether it will be a negative value or a positive value. So first off, though, if we actually increase the order, which means by default you're decreasing the disorder, however you want to think about it, order or disorder, we would actually see the delta S decrease. And what that means is the delta S would actually be a more negative number. So in a situation where we actually are creating more order, less disorder, we actually will see the delta S become a more negative number. The opposite is true. If we kind of go crazy with the disorder, things are all crazy and everything like that, or decrease the order, we actually will see an increase in the entropy value, and we would see a more positive value for delta S. So we'll actually see a more positive value there for delta S. So that's a little different than some things, oftentimes, for example, like delta H, we think about negative delta H, we think about exothermic, we think about perhaps that's going to be a more reaction that's going to occur. But here again, if we increase the disorder, we're actually going to be making a more positive delta S value versus our negative delta S, where we're creating a lot more order. One way you could calculate delta S is basically to take the delta S of your final state minus your initial states. And basically what that means is delta S would be our delta S of our products minus the delta S of our reactants. Why is that? Well, when we think about a chemical sort of reaction, we have reactants that go to products. So really products are our final state, right? And reactants are our initial state. So that's why we take our final minus our initial, sort of where we ended up. And that's why on all these things, just like what we did with delta H, for example, we take our products minus our reactants, and that basically gives us the difference between the final state and the initial state. And again, in terms of our delta S value here. Any questions on that there? Now, when we talk about sort of disorder and more disorder or less disorder, more order or less order, and by the way, I might, if I were you, maybe pick one of those sort of words there, in the sense of either think about entropy as either increasing the order or decreasing the order, or think about entropy as probably increasing the disorder or decreasing the disorder. Again, sometimes when people think about both of those words, sometimes people get very confused about, sort of what's happening. So, either think about it in terms of the order, or think about it in terms of the craziness and disorder, whichever way you want to think about it. It's probably a good way to do that. But when we're thinking about it in terms of, say, disorder, for example, where can we see sort of an example of this sort of in chemistry, and where do we see a lot of an example of this? And we actually see an example of order increasing or decreasing by looking at when we actually change states. So if we think about the states of things, when we're in the solid state, right, everybody's packed in there pretty tight to each other, all pretty nicely ordered. For example, if you had like a ionic solid, that's a very ordered sort of arrangement of how everything's together. When we go from, say, solid to liquid, everybody's packed in there fairly tight, but a little bit more room for movement, right? So if we just think about the comparisons of a solid to a liquid, solid's really not moving around a lot, right? It's like, obviously solid is pretty rigid. When you get to a liquid, it's obviously has some fluid motion, right? It's moving around. There's a lot more sort of activity happening. The molecules or atoms have enough energy to kind of get past each other and move past each other, which again is why things are more into sort of a fluid state in the liquid. And then obviously when we get to the gas state here, that's the liquid, we have completely broken apart from everybody, and everybody basically is flying around, right? They're flying around freely. You just got to think about it like that. That's a lot of disorder happening in front of my face, and things are moving around and stuff and creating a lot of disorder. So a very common place where we could kind of see this sort of change in entropy or the change in disorder is just by looking at things going from one state to the next, and that's a very common thing. So if the change from the initial to the final results in an increase in randomness, we would expect the delta S value to be a positive number. And again, if we kind of create a lot more order, we would expect it to be a negative number. And as I mentioned before here just a second ago, again, we see a lot of that with changes of state. So obviously solid is less than liquid, and there's the most disorder obviously in the gas state as everybody is flying around and creating sort of craziness. Another important thing to keep in mind, and we'll mention this a couple of times along the way, is actually units of these guys in terms of these thermodynamic sort of values. And delta H, if you remember, which is our enthalpy, usually has units of kilojoules. Delta S, which is our entropy, usually has units of joules. So there are going to be some formulas where we will use these guys together. And when we use these guys together in a formula, we do want to be really careful about units. Otherwise, again, if you don't do some proper conversions as you're kind of using these guys together, you will end up with obviously the wrong answer. You'll be off by that factor of 1,000. That would be happening. So let's talk a little bit more about disorder and sort of what's happening here. By the way, here, just looking at an example here, if we looked at water from our ice basically to our liquid water here, we're obviously making a lot more disorder. Here we would expect a delta S to be a positive value. Again, going from our initial state to our final state here, we're increasing the disorder. Now, talking about disorder, disorder really is related to the idea of probability. And a probable event is one where it could happen in many ways. So an improbable event is one in where, you could only really happen in a few ways. So for example, right, a probable event is, for example, if we were in a room and there was like 5 doors and we needed to get out of the room, clearly there's a pretty good chance, right? We open the doors, we walk out of the room, everybody gets out of the room. It's pretty probable we're going to basically get out. Now, if we were in the same room and there happened to be no doors, I'm not sure how we got in, by the way, but maybe there's just like one really small window way up high and we want to exit the room, clearly it's probably going to be improbable for yourself to get out, as there's only obviously one escape route, if you will. Now, when we think about, just sort of reactions, experiments, life, if you will, there's probably more ways to screw up something, right, than to do it right. And so it's a probable event a lot of times that things will not go right. There will be a lot more disorder happening. While, if there's only sort of one correct way to do something, it's maybe a little less improbable that everybody hits sort of the correct way all the time. So when we have a very ordered state, especially, in terms of maybe like, making a crystal, when things come into their solid sort of form and things like that, there's a low probability of that occurring, and we have a very small entropy as we increase that order. We have a much higher probability, again, like I mentioned, of, messing things up, if you will, or creating sort of a mess, if you will, and having a more disordered sort of property. And we have a much larger entropy value. Now, this is also sometimes related to what is referred to as microstates. And microstates are really just sort of some different ways that you can accomplish something. So, depending on how you want to accomplish something, W is really sort of the number of ways you could sort of achieve that. We sometimes get sort of the Boltzmann equation here, and these are some of these values. S is the entropy. W is the microstates. K is Boltzmann's constant, which is down here at the bottom. And when we think about sort of this equation here, and we think about, different ways of accomplishing something, we do get some ideas as to what's going to happen in terms of the entropy. So for example, if we have 4 circles, if you will, and we want to kind of put those circles either in one side of the box there or the other side of the box, there's really only one way in which you can achieve that. And either it will be on the left-hand side or the right-hand side is basically the only way you can do that. Now, if we wanted to take one circle and keep 3 circles on the other side of the box, there's actually 4 different ways you could do that. If we want kind of 2 circles in each box, there's 6 different ways of doing that. So what does that mean in terms of entropy, in terms of sort of probability and of things sort of happening? Well, if we kind of look at this Boltzmann equation and we really just kind of look at this part of it, since this is a constant, what we see is, for example, if our microstates was 1, like, hey, I got to get all 4 of those guys in one side, kind of like a carnival game, right? You got to throw all 4 balls on the one side into the holes. There's probably a very small probability that might occur. If we just look at it mathematically, that basically would be the natural log of 1. And as we know, when we take the natural log of 1, that does equal 0. So that would then obviously zero this whole thing out and give us really an S value of 0, which is a very low value for entropy. Now, if the carnival game was like, hey, just get 2 in either side, right? You probably have a much better chance at doing that. That's 6 different ways. If we do like the natural log of 6 on our calculator, for example, we get something like 1.79, which is a positive number. That times our constant would definitely give us a delta S value that is more positive and higher than it was when we had only one way of accomplishing that. So again, what we're seeing here in terms of microstates, for example, on the bottom there, where there's like 6 different ways you could accomplish something, much more ways of accomplishing it. It's a more probable event. It leads to a higher entropy, as opposed to you got to get them all on the one side in those 4 holes. It's a much lower probability that's going to happen and a much lower entropy in that particular case. Any questions on that? Here are some processes that we're probably familiar with that does lead to an increase in entropy. Again, here, these all lead to a positive delta S value that's going to occur. First one there we talked a little bit about is basically our solid going to liquid. So again, that process of melting, we're going from a state where we're in the solid, everything's very, very ordered, to a state where obviously we're starting to get things kind of moving away from each other, again having a little bit more energy as well, right? So when things get more energy, they're more apt to start moving around a lot more. They're able to pass through and pass each other a lot easier. um, we go from the liquid state obviously to the vapor state. We're increasing a lot more of the disorder and craziness of things flying around. When we actually make a solution, right? This is the two parts of a solution. We have our solute, which is the smaller part. We have our solvent, which is the larger part of a solution. But before we even do the dissolving process, right, the solvent itself is fairly ordered. You know, if you think about water, right, before you dissolve anything in water, there's a whole network of waters attached to other waters, right, through hydrogen bonding, a very nicely ordered sort of arrangement that's happening. In our ionic solid, for example, here in our solute, you know, there's a whole ordered arrangement of how our positive ions, negative ions, you know, are sort of by each other in this kind of three-dimensional crystal lattice. If you remember, maybe you talked about unit cells and that type of stuff in the previous class as well. Obviously, when we do that, we have to disrupt the order of the water and the solvent. We have to disrupt the order of these ions together, creating a lot more disorder, a lot more things sort of jumbled together over here, definitely increasing the amount of disorder that's going to happen. Temperature, again, relates really to sort of that energy is that we've been talking about a little bit here. Clearly, as I just mentioned, if you increase the temperature, what you're really doing, right, is adding more energy to everybody. You're giving everybody a lot more energy. So you would expect everybody to gain more energy. And just like, you know, the old saying, if you light a match underneath somebody, they're going to start moving. Same sort of idea here, right? If they increase the temperature, increase the energy that they're getting, they're going to start moving around a lot more. That's going to cause a lot more disorder from a lower temperature. And that's what we see here on the right-hand side. There we're at a higher temperature than we were on the left-hand side. And we would expect, again, the entropy to increase. So in all these cases, the delta S, or the change in entropy, would end up being, again, a positive value for each of these sort of systems, if you will. Any questions on that there? So let's take a look at a couple of examples here. How does the entropy of the system change for the following? And again, it's a good point to also talk about the idea of, again, system and surroundings. So what is the system? Well, really the system is anything you're sort of interested in. You know, when we do reactions or something like that, for example, the system is, say, the beaker. It could be the test tube, whatever it may be. And obviously the surroundings is everything outside of that. So, you know, for example, if you think about just an example of lighting a Bunsen burner and you got the flame burning, right? So the system there is the methane, the reaction that's causing that flame to occur. Basically everything on the outside of that, the air and everything that's surrounding it, is the surroundings. And we definitely can feel the energy change in the surroundings, right, as it's picking up all the heat and energy from that Bunsen burner basically lit and going off. So if we think about condensing water vapor, when we go through condensing, that means condensation. That means going from gas back to liquid. So again, we are going from a place of more disorder to a place of more order. So our disorder is decreasing, the randomness is decreasing, and we would expect this to yield us a negative value for our delta S. So why don't you take a moment and try the other ones here. So again, we would expect the randomness on this first one here to decrease, and we would expect the entropy to decrease as well. And again, our delta S would be a negative number less than 0. All right, take a second here for the other 3 and see what you come up with, and we'll talk about it. Okay, so let's take a look. So forming a sucrose crystal from a supersaturated solution. So the key on this one is really a crystal. So if you're familiar with crystals, they're really solids. They're very ordered type of situations. So clearly this is becoming a more ordered situation. And that basically means, by the way, going from a supersaturated solution, perhaps you may remember a supersaturated solution is one really where you have a solution that is has too much solute dissolved in it. It's very unstable. If you just kind of knock it or add like one little crystal to it, what you end up having is something going from an actual liquid or solution, and basically all the solid will come right out of the solution. And in that case, we're obviously going from a more disorder sort of situation to a more ordered situation. And again, that's sort of the same thing as above. We would expect the randomness to decrease, and we would also expect the entropy to decrease, and that again would result in our delta S becoming more negative or less than 0 in that particular case. Heating hydrogen gas from 60 again to 80 degrees, we have our hydrogen gas that's flying around, right? When we bump up the temperature there, it's gonna basically have a lot more energy, right? And be able to fly around a lot faster. That clearly is going to create a lot more disorder as it's flying around faster. And we would expect the randomness to increase. And that would then make our entropy increase. And remember, when our entropy increases, kind of different than a lot of thermodynamic values, it actually becomes more positive, in this case, are greater than 0. And lastly, sublimation, basically a dry ice. Sublimation is basically where we go from solid all the way to gas. We skip the whole liquid phase. So we're definitely going from more order over here to, again, gas molecules and more disorder on this side. Again, we would expect our randomness to increase, our entropy to increase, and our delta S value to be more positive or greater than 0. Any questions on any of those there? Okay. So let's take a look a little closer at entropy. First off, entropy, along with some other things, are what are referred to basically as state functions. And what are state functions? Well, state functions are something maybe you talked about when you talked about energy and enthalpy. But state functions basically are properties that are determined really by the state of the system. And it doesn't really matter sort of how you got there, right? So when we talk about sort of state functions, what we're really referring to is the idea that, you could take a scenic route to get to the top of the mountain, like we see on the bottom there. The guy in the red sort of took the nice scenic route around the mountain. You could take the more direct route on the mountain and get the blue sort of route to the top. In terms of something like potential energy, they both at this point basically possess the same potential energy. They're at the same location. And when we talk about really state functions, there's really 2 things that are important, sort of where you started with and where you ended up. And those are kind of the 2 important things here, the initial and sort of the final state. And that's why when we do something, say, like enthalpy, we take the delta H of our products, which is our final state, minus the delta H of our reactants, which is our initial state. So as we talked about just a second ago, thinking about a reaction, that's sort of what's happening here. As we go from reactants to products, again, our initial and our final state sort of happening. Now, there's also in a place where you can maybe remember this sort of aspect of it is the idea really behind Hess's law. If you remember what Hess's law was, right? It's basically where you take a bunch of like individual reactions, right? Kind of move them around, manipulate them, and then kind of add them together to get you to an overall reaction. And it's a reminder that not all reactions occur from straight reactants directly to products. some reactions, and even we talked about it in terms of kinetics, right? Some reactions happen in sort of multiple elementary steps, if you will, right? In order for that overall reaction to take place. And it doesn't matter if it takes you, 3 reactions, 4 reactions, 5 reactions. Ultimately, what matters is sort of your overall reaction, which is, again, where you started and sort of where you ended up, right? Everything else along the way is like intermediates, right? It's just kind of intermediate steps to get you there. And that's the same idea with things like energy, enthalpy, pressure, volume, temperature, and also entropy is also like that as well. Again, entropy is a state function, and it doesn't really matter sort of how you get there. It just matters where you end up. Now, entropy, like enthalpy, you could find a lot of values in a thermodynamics table, like in the back of your book, where you find delta H, delta S, and delta G type values. Let's talk a little bit about these sort of delta S values that you will find here. We just talked about it a second ago that unit-wise, there is a difference between delta H, which is typically given in kilojoules, and delta S, which is, again, typically given in joules. So as I mentioned earlier, and we'll see in this chapter, definitely an equation or two where both of these guys are present. So we do want to be really conscious of sort of our units when we're using these guys. Other sort of things that you might remember from delta H is if you have anything that's sort of in a standard state, kind of uncombined, typically it has a delta H value of 0 kilojoules, right? So things like H2, O2, etc. here. If you look it up in a delta H table, you typically will find a value of 0 for those guys. Now, if you look over here, this is a partial delta S table from your book here. And if we look at things, kind of like that, we have our H2 over here. We actually do have a value. We have our O2. We do have values for those. So that also is a little bit different than, say, delta H. You will find some values for entropy in that table. Also, for the most part, the entropy values, as you can see in that table, are positive values. So we typically will see these sort of positive values for entropy in this table. Like any thermodynamic sort of value that you're going to be looking up in a table, a reminder that it's always important not only to find sort of the substance that you're looking for, but it's also just as important or even more important to make sure that you find the correct state, right? Yeah. So for example, if you go to a table and you're looking up water, do you want it as liquid water? Do you want it as steam? Do you want it as ice? So you want to make sure that you look up the correct value, because obviously there will be different numbers in those tables depending on whether something is a gas, something is a liquid, something is a solid. So really important to, in any sort of thermodynamic table, when you look at things up, to make sure, again, that you not only find what you're looking for, but that it's in the correct state. And that's a very common sort of mistake that sometimes people make. They just look at the table and go, oh, I see what I'm looking for. That's good. And it's the first one in the table, but it's not the correct state, and you'll get sort of the wrong answer. So talking about thermodynamics, as I mentioned before, you probably previously really discussed the first law of thermodynamics, which is really all about that energy, like enthalpy, specific heat you probably talked about in that chapter as well. But the first law of thermodynamics, again, is that energy can be converted from one form to another, but cannot be created nor destroyed, right? And when we think about energy and we think about energy being transferred, we oftentimes, again, think about sort of that perfect situation where if something loses a certain amount of energy, say the system gives off 50 joules of energy, the surroundings are going to basically pick up 50 joules of energy. The difference is really just the sign, right? One will be negative in the exothermic sort of aspect. The other guy will pick up positive 50 in the endothermic process of it. Again, giving that idea of just energy really being converted from one place to the next or transferred from one place to the next, but again, not creating nor destroying. Here we're going to really talk a little bit about the second law of thermodynamics, which really deals with our entropy. And the entropy of the universe increases in a spontaneous process and decreases in or remains unchanged in an equilibrium process. So when we talk about entropy and we talk about sort of using it to determine whether or not a reaction is going to be spontaneous, we actually need to calculate the delta S of the universe. And the delta S of the universe is basically made up of two things. It is made up of the delta S of the system plus the delta S of the surroundings. And if we do that and calculate the delta S of the universe and it's greater than 0 or a positive number, then we would have a spontaneous process. Obviously, the opposite would be true. If we calculate the delta S of the universe and it's a negative number, then it would be a non-spontaneous process. If it equals 0, we're at equilibrium. So we're kind of equal in terms of the amount of disorder or spontaneity that's happening, right? That's basically kind of what equilibrium means, right? Equilibrium means, as we talked about, the rate of the forward reaction equals the rate of the reverse reaction. At that point, they're equal to each other. So everything is sort of balanced at that point, right? So there's no sort of reaction heading in one way versus the other. And that's what we mean when we sort of reach an equilibrium process when it equals 0. Now, a couple of things. First off, when we talk about the delta S of the system, as I mentioned before, that is also sometimes the delta S of the reaction, right? Is essentially what we're talking about. Now, you cannot make sort of the determination if a reaction is going to be spontaneous or not by simply looking at the system or looking at the surrounding. You do have to kind of put them together to get sort of the full picture of what is going on. And we're going to talk about it here in a second, how we go about sort of calculating each of those things. So let's talk about first the system, or really the reaction, right? Because again, what we're typically interested in terms of a system is the reaction that we're doing. So the way that we calculate the delta S for a system, or the delta S of a reaction, is we basically could go to a thermodynamic table like we just saw there, look up our delta S values for all of our products and subtract it from the delta S value from all of our reactants. So our delta S of our reaction here, again, our products, which is kind of our final state, minus our reactants. Just like what you would do in terms of delta H and maybe have done before, is you do need to take the coefficients into account. So for example, if I looked up the delta S value for A, imaginary A, and it was 20 joules, and our coefficient here was 2A, we would then, if we wanted the delta S value, need to go 2 times 20, which obviously would get us 40 kilojoules, actually joules, 40 joules in this case. So you do need to take the coefficients into account. So you basically add up all the delta S values you find in the table for the products. You then subtract them from all the delta S values you find for the reactants, again, taking the coefficients into account. Any questions on that there? So we have one here on the bottom. Here are some values that you would find from a thermodynamics table. So why don't you take a moment or two and see what you come up with for this reaction here. Okay, so again, just to be clear, if you have sort of a problem like this, and this is obviously the only thing given to you, if you're only given a reaction, and typically in a problem, if you're only given a reaction in a thermodynamics type property, that's a pretty good indication that you should go to the back of the book if they're not given to you and look up in a table your values and do sort of products minus reactants. And that pretty much holds true for a delta H type problem, a delta S problem, a delta G problem that we'll see. So again, we'll see some different sort of formulas as we go through this chapter. And sometimes people are confused about, sort of which formulas should you use. And sometimes you should always use sort of based on the information given to you. So again, in a problem where you're really not given much information other than the reaction, like I said, that's a pretty good sign that you should go to a table and look up these values. And again, that is where all these values would come from. So at this point, we're going to basically do our products minus our reactants here. So our delta S here of our system would be, starting on our product side there, we have 2 CO2s. So we would take 2 times the value of CO2 that we find in our table there. That takes care of all of our products. We then would subtract it from our reactants. Again, here we have a 2 for the CO, so we take 2 times the value of CO, which is 197.9. We're going to add it to the value of O2, which again, as I mentioned before, unlike delta H, you will find a value here, and that is 205.0 joules. And putting all that together there, we're going to end up with 2 times 213.6 minus 2 times 197.9 plus a 205. Looks like we get something like minus 173.6 there. Joules. First off, any question on sort of that calculation there? So what does this number mean? So just so we're clear, this number does not necessarily mean that this reaction is spontaneous or non-spontaneous. Remember here, we just calculated really the delta S of the system, not the universe. But it does actually tell us what is going on in this particular reaction. And in reality, we actually could have, before we did the calculation, made a pretty good assumption as to whether or not our entropy value would be positive or negative. So how could we have made that sort of assumption here by just simply looking at the equation? Well, if we look at the equation, gotta clean up the equation here for a sec. So if we look at the equation here and we look at actually gas molecules. So this guy is a gas, this guy is a gas. We have 2 gas molecules here, we have 1 gas molecule here, which means on our reactant side, we have basically 3 gas molecules, right? We look over here on our product side, we have 2 gas molecules sort of happening here. So in this reaction, what we actually see is we are going from a system where we started with 3 gas molecules to a product side or a final state where we ended up with only 2 gas molecules. So what does that mean in terms of sort of order? Well, we got 3 things flying around our face, and now we're going to only 2 things flying around our face. So we have a lot more order that's happening. So we went from a situation where we had a lot of things flying around to less things flying around, which is going to create a more ordered situation, which means in terms of the reaction, we would expect the entropy to actually start to decrease, which means when the entropy should decrease in this case, the delta S should be negative. And that's exactly what we see here as a result of our calculation. So you actually can look at the reaction that you're dealing with, and based on really, kind of gas molecules, if they're involved, if you go from something where you end up with more gas molecules than you started with, you would actually increase the entropy, and it should be a positive value on your calculation. If you are like in this situation here, goes from a situation where we go from more gas molecules to less gas molecules, then again, you would expect the entropy value to decrease and become more negative like we do see here. Question on that? So that's a really nice way that you can sort of use the reaction, even before you do the calculation, to sort of predict where you'll be, and also allow you to double check your calculation to make sure perhaps you didn't make any type of mistake. And again, that's basically what it says here. If we end up again with more gas molecules, we definitely have a lot more things flying around, a lot more disorder happening. If we end up with less gas molecules, we have less things flying around, a little bit more order. If there's really no net change in terms of the gas molecules, then you could have either a positive or negative delta S value, but it will be probably a relatively small number, as there's kind of no big change that's sort of occurring. So take a second here, and based on the reaction on the bottom there, would we predict the entropy change to be a positive or negative value? So sort of applying the same approach that we were just talking about, looking on the reactant side, there's a grand total of only one gas molecule right there. On the product side, it's all solid, so there are no gas molecules. And what that means is we would predict in this case that the entropy is decreasing, and we would predict that the delta S value should be negative in this particular case. Any questions on that particular one? By the way, in this chapter, you will come across a lot of questions sort of like that. It's very common in sort of thermodynamics type properties that are problems that they actually don't give you numbers sometimes. They just go, hey, this guy's positive and this guy's negative, at 25 degrees Celsius. Do you think it's going to be spontaneous or non-spontaneous? So there are a lot of questions in sort of this thermodynamics chapter where, they don't necessarily give you information other than maybe what the signs of certain things are. And based on that, you should be able to predict if the reaction would be perhaps spontaneous or non-spontaneous. You could always, in those type of problems, just put in fake numbers and kind of do a calculation, but it's a very common sort of question that's asked. So that is the delta S of the system, or delta S of the reaction. We're now going to talk about sort of the other part of the delta S of the universe, which is now the delta S of the surroundings. So delta S of the surroundings is related to enthalpy, and it is related to whether or not the process is a exothermic process or an endothermic process. So let's take a look at on the left there. So we have a flask there, and it's an exothermic process. So what does that mean? Well, it means that this system here is giving off a lot of heat and energy. And our surroundings here is pretty much the guys that are going to pick up all that heat and energy, right? That means, by the way, the delta H here is negative. And when it does so, that obviously, imagine anybody that's in the surroundings is going to pick up that energy, going to have a lot more energy. And we would expect the effect on the actual surroundings to increase the entropy, right? They're going to pick up that energy. They're going to be flying around a lot faster if they're gases. They're going to have more energy, going to create a lot more disorder. We would expect it to become positive in that particular case. What happens if we have sort of the opposite here, which is an endothermic process? Here our delta H is positive. The system in this case is actually going to pick up all the energy from the surroundings, or some of the energy from the surroundings. What is that effect in terms of the surroundings and its delta S process? Well, if the surroundings are losing energy, if you just think about gases, for example, they're going to now be moving around a lot slower, right? So there's a lot more order sort of happening here in the surroundings as the surroundings basically loses that energy. We would then expect more order in the surroundings. That would mean our delta S of the surroundings would be less than 0, and we would expect a negative value here for our delta S of the surroundings. Any questions on that? So there actually is a relationship between, again, the surroundings and, as you can see, the delta H value. And that relationship is that the delta S of the surroundings is proportional. That's what that little guy here means, proportional. proportional to minus delta H of the system. So what does that mean? Well, we can make a simple little table, if you will. We take the delta H of the system, and we take our delta S of the surroundings equals minus delta H of the system. In a exothermic process, our delta H would be negative, which means our delta S of the surroundings would be negative of the delta H value, where our delta H is negative. So negative and negative will turn our delta S of the surroundings into a positive number, which is sort of what we see here. In an endothermic process, it's going to be positive, which means our surroundings is negative the delta H, so negative of a positive gives us a negative value for our delta S of the surroundings, which again is what we see happening here. So the delta S of the surroundings, again, is obviously affected by the energy. And again, it's sort of an opposite relationship to the energy as to what we end up with our delta S. And again, our delta S becoming more positive means a lot more disorders occurring. Question on that. Now, does the temperature of the surroundings have an effect on the entropy change that we would see? And the answer is yes, it does. So, for example, let's just say that our surroundings is at a really high temperature. So out here is at a very high temperature. If our surroundings is already at a really high temperature, for example, the energy that's coming off from the reaction that's adding to our surroundings is probably not going to make that much of a dramatic effect because our surroundings are already super high, right? So that energy that's coming off from the reaction is going to add to it. But overall, we already started at such a high level of craziness that the extra energy coming in is probably not going to make that tremendous amount of difference. So like an example, if you lit just a match or something like that out in room temperature, if you will, right? And you kind of put your hand near the match, right? Be careful, don't do that. Obviously, don't play with fire. But you would feel the heat coming off, right, of the flame and stuff like that. Now, again, if you took that same one match and if you put your hand again near that one match, it gets pretty warm, right? You can feel a pretty good amount of heat coming off of it. Again, don't play with fire. But if you then took that one match and you lit it and perhaps you put it into a pizza oven that's 600 degrees or something like that, right? And again, don't do this either in case you have a pizza oven or a regular oven, don't do this as well. But again, if you put that one match sort of lit inside that environment that's so hot to begin with, really the heat coming off of that one match is probably not going to contribute super much or make a super change to the environment in which it's in. And that's sort of the same idea here. If you kind of already are starting pretty high, even though it is obviously contributing, it's not going to make a tremendous difference in sort of the entropy change that you would see because you started at such a high sort of value to begin with. Any questions on that? And again, don't play with fire. All right. So how do we sort of, come back. How do we figure out the change in entropy for the surroundings? Again, it is related to our delta H value. And as I mentioned just a second ago, again, the temperature of the surroundings does have an effect, especially in an exothermic sort of process. If it's a low temperature in the surroundings, then obviously that exothermic process would give off a good amount of heat and energy and make a pretty significant change to the delta S of our surroundings. Again, if we're pretty high in temperature, the entropy change is going to be relatively small for any type of exothermic reaction. So it got a little messed up down here, so let me rewrite it up on top. The delta S of the surroundings is equal to minus delta H of the system, or the reaction, divided by our temperature. So a couple important things here. Obviously, the negative here is what we were just talking about, sort of that opposite relationship. Um, Also down here, this is our temperature that does need to be in Kelvin at that point. And using our surroundings calculation there with what we just talked about for our system previous, where we take the delta S of our products minus the delta S of our reactants. We now know how to calculate both things here to figure out the delta S of the universe, which again is our delta S of our system plus the delta S of our surroundings. And remember, it is this guy's value here being positive or negative, which helps us determine whether or not a reaction will be spontaneous. Now, I will give you sort of a cautionary note. Again, I've been talking a little bit about units. Delta H's, again, here are typically going to be in kilojoules. When you look up in that table like we did in the previous example, I guess I should point to the right thing here. We'll go this guy. This guy is typically going to be in joules, which means when you come down here to add them together, if you're not careful and you leave this guy in kilojoules and you add it to the other guy that's in joules, again, you're going to be off. So using the surrounding answer and using the system answer will usually require some type of conversion either to joules or to kilojoules, but most people might go to joules on this because, again, delta S is typically given in joules. So again, you just got to watch those units in this particular case. Any questions on that there? Okay, so why don't we try one here and see what you come up with. Here's all the values, again, that you shouldn't need in this one. We want to calculate the delta S of the system, the surroundings, and we want to know, is basically the synthesis of ammonia a spontaneous reaction or not? So there's some of your delta S values on the bottom and your delta H value there for the reaction. So take a second and see what you come up with. Okay, so let's take a look and see how we're doing. So in this case, we do want to find both the system and the surroundings. So remember, for our system here is going to be really our products minus our reactants. We would go to the table if it was not provided for us. And again, that is basically where all of those values came from. While our surroundings, right, so our system here is delta S of our products minus our delta S of our reactants. And our surrounding is our delta S of the surroundings equal minus delta H over T. Here's our delta H value here. So we really do have, pretty much everything that we need. So let's see what we end up with here. So starting with our system, remember, we want to do products minus reactants. We also want to make sure that we do take into account, obviously, the coefficient. So starting on our product side, we have a 2 there in front of the NH3. So we take 2 times the NH3 value. That takes care of all of our products minus our reactants. We have a 1 there for our N2, which is 192, plus our 3 times our H2 value, which is 131. That's going to yield us here, let's see, 2 times 193 minus 192 plus 3 times 131, looking like a minus 199 joules in this case. First off, any questions on that calculation there? Does that calculation make sense based on the reaction that we see? What this is telling us is this is negative, which means the reaction is actually decreasing in entropy or disorder. And we see that by looking here, we have 4 gas molecules on the left-hand side We have two gas molecules on the right-hand side. We would predict that this should give us a negative delta S for our system here, and it does. Also, a reminder that this does not tell us necessarily that this reaction is non-spontaneous, because the delta S here is negative for the system. So remember, we need to get to the universe really to determine that. So the other aspect of the universe is the surroundings. So here we are given the delta H value. So this is again negative 92.6. I'm going to multiply it by 1,000 because I know I'm going to add it together, and that will convert it into joules for me. Also, 25 degrees Celsius means that we have 298 Kelvin, which should go down there on the bottom. That gives us our surroundings of 92.6 times 1,000 divided by 298, going to give us a positive, we'll call it 311, and because I converted into joules, it would be 311 joules for our surroundings. Again, here, if you left it in kilojoules, you're looking at, I believe, we got there 0.311 kilojoules. Now, does this make sense? Well, we are saying that the surroundings here are increasing in entropy. There's an increase in disorder. We would expect that because our delta H here is negative, and it's a regular temperature, not really high, not really low, kind of normal temperature. And remember, the relationship is that the delta H, or the delta S of the surroundings, is basically negative of the delta H. So negative and negative does yield us an increase in entropy of our surroundings. So again, that does make sense as well. Any questions on that? So to determine if this guy is going to be spontaneous, we really need to put both of those numbers together to figure out the universe, which again is our system plus our surroundings. And here our system is minus 199 joules. And again, because I converted this into joules, I'm good to go by adding the 311 to that. And that's going to yield us, I believe, 112, right? 112 joules for the delta S of the universe. This is now a positive number, which means the delta S of the universe is positive, which means that this reaction would be spontaneous because of that. Question on that there, or any part of that? By the way, this reaction is spontaneous. And again, and this is a very good example of spontaneous does not necessarily mean fast. It's actually a very slow reaction unless you use a catalyst, which is commonly used. Otherwise, it actually occurs very slowly. But the use of a catalyst helps speeds up this reaction. But again, the idea here, spontaneity, is not fast or slow, but will it actually occur? And again, the answer here would be yes in this particular case. Any questions on any part of that calculation? One last note here to finish up on, and it does deal with this equation, since we've been talking about this equation here, which is our delta S of our surroundings. Now, this delta S of our surroundings formula is to be used with, obviously, calculating the delta S of the surroundings. And what I mean by that is later on in this chapter, we will see a formula that pretty much looks identical to this. The only difference is there's no negative. So keep that in mind as we go through this chapter. You'll see something, we'll rearrange an equation, we'll get something that looks almost perfectly identical to this equation, but again, it will be lacking the negative sign. So good way to remember it is if you're calculating delta S of the surroundings, you need that negative sign. So that's a good way to remember it. If you're kind of getting to this equation, as we will do later on in this chapter, through sort of rearranging another equation, there is no negative sign. So the negative sign is oftentimes missed here with this equation, and sometimes put in where it shouldn't be later on. So just keep that in mind. That's again a common sort of error that sometimes people make. All right. What I think we'll do then is